Learning agents offer a dynamic alternative to traditional scripted behaviors. Instead of relying solely on predefined actions, we train these agents in simulated environments to develop complex, adaptive behaviors that can respond to unpredictable scenarios and unique player interactions. This approach can result in more engaging, flexible, less repetitive gameplay that challenges players in interesting ways, while also reducing the burden of heavy manual scripting as AI complexity increases. Some possible use cases that you can consider include in FPSs, creating bots that use tactics like flanking, suppression, and cover for more engaging and immersive combat. For RTSs, agents can be competitive opponents, fully managing units, resources, and making strategic and tactical decisions just like real players. In racing games, real-life telemetry data from professional drivers is used to train AI, allowing non-human opponents to effectively replicate real-life driving styles. And in academia, there are many usages of reinforcement learning in simulation platforms. For example, mimicking schooling fish to explore topics such as decentralized decision making. So today, we're going to be building a simple reinforcement learning example by training Unreal's default third-person character to navigate to a location using a reinforcement learning framework. The purpose of this example is to show you the basics of implementing the framework, and the general idea of how deep reinforcement learning is used to achieve a certain behavior. We will be using a reinforcement learning library I developed, which can be found at the GitHub link on screen and in the description. Really quickly, let's go over the architecture. The library is split into two parts, an external Python module, which contains our training algorithm and script, and an Unreal plugin, which will help us set up the training environment inside the Unreal editor. The parts communicate via a TCP tunnel, but you don't have to worry about it, as the library handles all the underlying details. Your main concern will be implementing the classes and methods given in the Unreal plugin to create the training environment. The Unreal plugin supports both C++ and visual scripting, so don't be afraid to continue even if you don't have any prior programming experience. At a high level, our training pipeline works like this. The current state of the environment is sent from our Unreal simulation to the Python module. The model analyzes this information, selects what it believes is the best move, and sends it back to Unreal. Unreal executes the move and then returns a reward to the Python module, indicating how effective the move was, along with returning the new state of the environment. This forms a loop, which we repeat, sending data and actions back and forth, guiding the model's learning process, teaching it what moves are good and what moves are bad. With an overview out of the way, let's get started. First, let's create our Unreal project. As mentioned, we will be using the provided third-person game template, so go ahead and create a C++ project with that template. Once your project is created, please make sure to follow the setup instructions for the plugin on the GitHub page before we continue with this video. If you have any issues with the plugin, please let me know. Continuing, let's open up the project and start setting up our simulation. So, reviewing our goal again, we want to teach our third-person character, whose blueprint we have here, how to move to a location we set inside this map. First, I'm going to remove these movable blocks, just to simplify the environment a little. We're also going to remove the default player spawn, as we're going to want to spawn the player character ourselves so that we have full control over its lifecycle. So, what do we need to start training? The development process for this framework is pretty simple and streamlined. All training is essentially managed by the RL-based bridge class. To utilize it, we create a subclass and implement its abstract methods. These methods form the core of the training loop we talked about earlier, and where you'll incorporate your own custom logic to dictate the training process and achieve your desired behavior. The lifecycle of our environment and training will be handled inside the level blueprint. Here, we will initialize our RL-based bridge subclass, spawn the actors and obstacles necessary for simulation, connect to the Python module, and ultimately begin training. Think of each level as a lesson. We want to design the environment such that we teach some sort of behavior in each one. Each one should be a scenario with some sort of goal for our learning agents to discover and achieve. Right, so let's start with the level blueprint. First, let's set up our environment. Let's think about all the relevant actors that we want to maintain and utilize in this simulation. In this example, all we're going to do is spawn our third-person character using the spawn actor blueprint. I'm going to spawn it at 200, 1500, 100, but you can choose your own coordinates as long as the character spawns within the map. Next, possess it with the player controller so it will respond to input. In this case, our environment is pretty simple. In the future, you can add more actors here, but for the sake of this example, that's all we need to know for now. So with our simulation environment ready, let's construct our RL-based bridge object inside the level to manage our training. We want to create and use a subclass of RL-based bridge, implemented with our own custom logic. So let's go do that now so we can select that in the class menu. Don't forget to save after editing your blueprints. Make sure you have plugin content enabled in your content browser. You can find the C++ class for RL-based bridge here. Today, we're going to use the UObject version. Right-click and create blueprint class. You can put it wherever you want. I'm going to store it inside the blueprint folder under the third person folder. Perfect. Once that's created, let's open up the blueprint and take a look at the methods we need to implement. If we take a look at the left-hand side, we can see the functions we mentioned earlier that we need to override. Create state string, calculate reward, handle reset, handle response actions, and is action running. Go ahead and override them. Next, define a class variable called controlled pawn. This references how we will access information from our third-person character and execute actions. We will set up the relationship later, back in the level blueprint. We'll start with some of the easier functions and work our way up to the more complex ones. First, let's start with handle reset. As part of the training process, we will need to reset the simulation back to a starting state so the model can retry and continue to learn. Resets will occur when the model either succeeds and reaches our designated goal, or takes too long to reach the goal, so we have to start it from scratch. In our case, our handle reset function is extremely simple. All we need to do is reset the third-person character's location back to its initial spawn. In my case, this will be 200, 1500, 100 for XYZ. Next, create state string. In this function, our objective is to generate a message that contains all the environment information that we want our model to use to make its next decisions. This is called the observation state. So what information should we include exactly? Should we include as much information from the environment as possible? Is there information the model shouldn't know? If you were the model, what do you think you would need to know to make a good decision in this scenario? In the end, this isn't an easy question to answer, especially as your desired behavior gets more complex. Don't be afraid to be wrong. Come back later, adjust this function, and experiment with different data to see how your model reacts. So for our third-person character, what do we need? Well, we just want our character to move to a cell location on a map where the layout never changes. It turns out, providing only the character's current position is enough. This is because, over many training iterations, the model will learn how the map layout relates to its current position, memorizing obstacles and boundaries. We will use one of the helpers in our library to create the state string. Append vector to state string takes a 3D vector and adds it to the end of the state string with the proper format for our framework. Since there are no other values, the base string is empty. In the handle response actions method, we're going to execute the decisions made by our model and perform corresponding actions in the simulation. These decisions come in as an array of floats ranging from -1 to 1. Think of each index representing a specific character action or feature of an action. We need to create a mapping of these array indices to character actions in our blueprint. The default third-person character has two movement options. It can jump, using the jump function, and it can run in a direction using the add movement input function. For jumping, it's straightforward. We'll look at one specific index in our array, let's say index 0, and if the value there is greater than 0, we call the jump function. Next up, for running, which is the add movement input function, this action is a little more involved since it requires us to specify a direction vector and a scale value. We'll represent the two-dimensional direction vector using indices 1 and 2 in the array, corresponding to the x and y axes. The scale value, which controls how fast our character moves, will be directly taken from index 3 since it naturally ranges from -1 to 1. Finally, because add movement input was meant for continuous player input, this design will complicate our handle response actions logic slightly. We will see how we can handle this behavior later. We'll use one more index, index 4, to indicate how many frames the movement input should be applied. So the first thing we need to do is parse the actions array, which is initially given to us as a string. We can use the parse action string function, which converts the string to our desired float array. Next, let's get the values from our indices as shown in the previous slide. Let's start translating these indices to inputs as previously discussed, starting with jump. Simply check if the value retrieved is larger than 0. If it is, call the jump function. For add movement input, as discussed earlier, the call to the function will be more complicated due to the nature of its design, where it's meant to be held for a number of frames to accelerate the character. We're going to handle add movement input differently from jump. Instead of calling it inside handle response actions, we're going to save its input values as class variables and use them to call add movement input inside our next function, isActionRunning. For world direction, we'll create a 2D vector using indices 1 and 2 from our array and then normalize it to produce a unit vector. Next, let's save scale. Simply store the value at index 3 directly. Finally, create a variable called framesHeld. To calculate its value, multiply the float at index 4 by a chosen number, which represents the maximum duration in frames that our third-person character can continuously call add movement input. I'm using 30 frames, but feel free to choose another value. I suggest that your chosen number is at least 15 frames to make sure the character gains enough acceleration to actually move from its starting position and make meaningful movements each training step. After calculating, take the absolute value of the result and store it in framesHeld. With handle response actions now complete, let's move on to isActionRunning. The purpose of the isActionRunning function is to let the training manager know when the actions given by the model have been fully executed inside the simulation, and the training process can proceed with calculating the reward and new observation state. Simply, when we are still applying the actions in our simulation, return true. If we're ready for new actions, return false. Right, so as mentioned before, add movement input spans across multiple frames. We will handle it here and return false once all the frames it was assigned have completed. Check if the number of frames held is currently above 0. If false, we can return false since there are no more frames left and thus we have finished executing our actions. Otherwise, we're going to call add movement input with our stored values, subtract a frame from frames held, and return true. Great, so we finally reached the last function to implement. Just a little further and we'll be good to go. So calculate reward, as the name suggests, calculates the reward for the current state and determines if the current training episode has concluded, indicating if the environment needs to be reset. This function is crucial because it directly influences how our learning agent learns during training. By assigning positive reward for desired actions, we encourage the agent to repeat them, while penalties or lower rewards help discourage unwanted actions. We also check if the current episode of our training process has concluded. That is, if the simulation has reached an end condition requiring an environment reset. Generally, there are 3 scenarios for episode termination. The agent successfully reaches the goal, the agent triggers a failure condition, or the maximum step limit per episode is reached. Make sure you clearly define your episode termination criteria before you start developing, as it'll make reasoning about your logic easier as you design the reward function. You'll probably spend a lot of time here again, playing with different reward logic. Again, machine learning is all trial and error, so don't expect your behavior to be perfect on the first try. Do what you think might work, and then come back and adjust when it doesn't. So how should we implement this function for our example? I'm sure I've said it enough now, but our goal is to get our character to learn how to navigate from its spawn point to a set location on the map. I'm going to pick mine at 1470, 1970, and 250. To achieve this behavior, we're going to reward the model for getting the character closer to the goal in every action, and provide a large positive reward for actually reaching the goal itself. At the same time, we'll penalize actions that move the character away from the goal. We'll also penalize the model for taking too long to reach the goal by adding a small cost per step. Lastly, we'll terminate the episode of the characters within 300 units of the goal, which we'll call a success. Otherwise, the episode will time out when it has run for 128 steps. To make it more clear what our function will look like, let's go through our logic as a visual example, which we'll later implement directly in blueprints. First, we calculate the reward based on how much closer the character moved towards the goal since its last action, subtracting a fixed step cost to encourage the model not to dawdle. From here, our logic branches into 2 distinct paths. If the character is within 300 units of the goal, we consider this a successful episode. Reward the agent with a large positive bonus, reset the step count, and end the episode. On the other hand, if the character is further than 300 units, so outside the goal zone, we haven't succeeded yet, so we'll want to check how many steps it's been since the start of the episode. If the steps taken are less than 128, the episode continues, allowing the agent to keep trying. While if the steps taken are 128 or more, then we want to terminate the episode. Timeout ensures episodes don't run indefinitely if the agent gets stuck in part of the map. Let's get this implemented in Blueprints. First, we're going to create a new local variable, which we will use to store the calculated value of the reward in the function. We're also going to create two new class variables: previous distance, which will be the distance of the actor from the goal in the last training step, and steps, which will be the number of steps the episode has been running for. These need to be class variables, as they need to carry over to the next training step. Let's follow the visual example to guide us through this implementation. First, let's find the distance from the actor to the goal. Then, calculate the current reward by subtracting the previous distance by the current distance and applying a step cost of 10. Let's save that reward in the variable we made. We'll also save the current distance as previous distance for the next training step. Next, we're going to create our first branch. If the distance is less than equal to 300, we follow the left branch of the tree. Reset the step counter by setting it to 0. Add 500 to the reward before returning it, and return that the episode has concluded as well. If the distance is larger than 300, then we need to branch again and check the current number of steps. If less than 128, add 1 to the number of steps, return the current reward, and that the episode is not concluded. Otherwise, the episode is timed out. Reset the step counter to 0, return the current reward, and that the episode is concluded. Great, we're finished calculating reward, but really quickly, we need to go back and add one more piece of logic to the handle reset function because of how we're using the previous distance variable. When we reset the simulation, the previous distance value carries over, so our first training step in the new episode will be using the previous distance value from the last episode. This can mess with our reward, so when we call reset, let's make sure to properly reinitialize the previous distance value. Perfect! We've implemented all 5 of the necessary functions for the training loop, and we're almost ready to start training. Let's go back and finish constructing the level blueprint. Returning to our level blueprint from earlier, we can now select VP Bridge Object as an object to construct. Next, we need to pass the spawn 3D character actor to the bridge as our controlled pawn. Doing this ensures all references to controlled pawn we previously used when implementing our functions will correctly point to this actor. Now, we'll call the connect function from the bridge. This function creates a socket that waits for the Python module to connect, setting up a TCP tunnel that enables information to flow between both modules. By default, the socket is set up on localhost 127.0.0.1 at port 7777. We'll also pass in the information that the Python module needs to run, specifically the action and observation space size. These values are derived from the number of values you extract from your action string and handle response actions, and how many values you add to the state string and create state string. In our case, for the action space, we have 5 action values: the jump value, the x and y coordinates for our direction vector, scale, and the number of frames held. While the observation space only holds 3 values, just the xyz coordinates of our actor. Finally, the last thing we have to do is call the start training function from our bridge object, and that's it. We've officially finished implementing the framework and we're ready to start training. Before we start training, let's quickly review the training script located in the Python module. The script sets up your environment and defines a set of constants at the top of the file, values you might recognize from previous machine learning projects. Hyperparameter tuning is a critical step in any machine learning workflow. By tweaking parameters such as the learning rate, discount factor, and batch size, you can optimize your model's performance and convergence. By default, the script leverages stable baselines 3 for its deep learning algorithm implementations. In this example, we will be using Proximal Policy Optimization, PPO, a solid baseline training algorithm. I recommend checking out the Stable Baselines 3 website. Their documentation offers deeper insights into how these constants influence training dynamics and overall model behavior. You can also try implementing algorithms from other libraries, such as rlib, or, if you have the expertise, create your own custom reinforcement learning algorithms. Back in our editor, I've added a cube above the location of our goal, just to make it easier to visually identify how close our character is to it. I also added a little ramp, just to make it easier for our character to make it up to the goal. To start training, simply click play. You'll see the Unreal Editor seize as it waits for our Python module to connect. So open the library in your File Explorer, enter the Python directory, right-click and open a terminal. To start the Python module, simply run the command python-train.py. As you can see, the Python module will start and after a few seconds, connect to the socket created by our Unreal plugin. And just like that, we're training. You'll see our character begin to move and jump around as the model tries to figure out what series of actions it needs to use to get it closer to the goal. You can see the training loop in action in the terminal we opened, where we're receiving our observation state and sending action strings back. To summarize, we set up the training environment in the level blueprint, implemented our deep learning framework by overriding functions in the RL-based bridge class, and learned how to start our training loop. These are the foundational steps to utilize the library, and I hope you're able to take what you learned in this video to expand and explore. If you would like further guidance and want to see other usage examples, be sure to explore the other videos in the playlist linked in the video description and visit the GitHub page for documentation and updates. Good luck!